welcome back. We were continuing our discussion on photolithography, and we just got started with the discussions, and we will continue with some more detailed aspects of photolithography in this particular class. So, probably all of you now remember that we talked about this particular animation, or we showed this animation in some of our at some point in the previous lecture. So, the different steps of photolithography, what we understand so far is first you take a p-type or a doped silicon substrate, then the next stage is you sort of grow the silicon oxide layer, which we also refer to as the barrier layer. Then we coat the what is known as photoresist. We just started talking about it. Today's discussion will focus more on the photoresist. We will not go into the too much of photoresist chemistry, but I will still give you an idea about the photoresist tones and how exactly a photoresist works. And then we started talking about the mask, which actually contains your original design, which you would like to replicate on your photolithography or on your photoresist layer, or you sort of want to get a copy of that on the photoresist layer. And then once you place the mask, you do an UV exposure. This is exactly the optical source we talk about, and it is essentially because of this step the technique derives its name photolithography, because whatever change in property you achieve in the photoresist layer is due to exposure to light, and in most practical cases the light source used is UV. The only reason is that ultraviolet rays have wavelength which is smaller than visible light, and smaller the wavelength it is better for replicating the structures. We will talk about it in somewhat details. Once UV exposure is done, then of course there is, depending on the tone of the photoresist, there is preferential curing or disintegration or degradation. Then the mask is removed, and then you apply different thinners or different chemicals to etch first the photoresist layer, then you also etch the oxide layer, so that for your diffusion reaction, which is sort of going to create the other type of doping in the wafer, let us say over these areas, if you sort of have started with a p type wafer, you would like to dope it with something n type, so that you have p-n junctions. So, first you sort of etch the photoresist layer, then you also etch the oxide layer, maybe with hydrofluoric acid, and then if the photoresist layer remains present during the diffusion reaction, this might also get, the polymer layer might get contaminated, and some chemicals from the polymer layer or the photoresist layer might also react with the surface, because it is a liquid state reaction of the photoresist layer as well before your doping reaction starts. So, that is precisely what is done. The photoresist layer is also removed, and then you do the doping reaction, and finally you get rid of your oxide layer itself. Of course, for all practical purpose, this is followed by another process of metallization. Okay, so we will, as I told you, we will sort of talk, limit our discussion more into the periphery, and I will sort of highlight you about the major steps rather than going into too much details. You may recall that we started to talk about what is a mask and how exactly it works. So, you essentially have a piece or a flat object which has some slits which allows the light to pass. So, this is the design. So, first the mask has to be fabricated, and then you place this mask on a photoresist coated wafer, you allow the light or shine light over it. All these areas sort of absorb the light, it does not allow the light to pass. Only these areas, the so called slits, they allow the light to pass. So, essentially based on that, the areas which are below these openings, there is a change in the property of the photoresist layer due to its interaction with the light which is shining on it, and therefore, the mask pattern eventually gets transferred onto the photoresist layer. So, at this point it is important to, and it becomes important to understand what photoresist is. I briefly have told you that these are some sort of a photosensitive polymers. Of course, there is a lot of research that goes on into photoresist chemistry. For our discussion will be more from the engineering aspects. So, we will skip all the details, but still some of the basic aspects you need to know, particularly the photoresist tones. So, as I told you, the several steps which are sort of are sub steps of the entire photolithography process, for example, dehydration and priming, resist coating, soft baking, exposure, development and post development inspection. So, it is up to essentially right after cleaning of the of the silicon wafer down to the step before you sort of dope it or dope with the other type of dopant. All the intermediate steps are part of the photoresist processing. So, let us get started with what are the steps, but before that let us have a look at what exactly a photoresist means. It is a special class of photosensitive polymers and photoresist layer polymer, and a photoresist layer has two basic functions. Firstly, it helps in the precise pattern formation, and secondly the protection of the substrate from chemical attack during the etching process. Now, what exactly is the etching process and how it works, you have to wait for some more time to get an idea about it. Typically a photoresist consists of three components. Firstly, the resin, which is a type of a polymer which serves as the binder of the film. So, this is the essentially base polymer matrix. The inhibitor or the sensitizer, which is the photoactive ingredient. So, it is essentially not the entire part of the polymer sort of reacts in the photosensitivity, I mean photo reaction. You have some inhibitor or sensitizer present within the matrix, which is the photoactive ingredient, and the solvent which keeps the resist in liquid state until it is processed. So, this is another thing, I mean if you sort of have only the resin and the inhibitor, for example, the resulting material will be very high viscosity material. It will be difficult to apply. You just saw there is a step called photoresist application. So, the photoresist application will be very difficult. So, typically what is done for preferential application, essentially application here means that the photoresist layer will be uniformly coated in the form of a film or a thin film on your silicon wafer, on your cleaned primed and dehydrated silicon wafer substrate. Now, this is not done manually or by something like a brush, but this is also done by a technique called spin coating, which we will discuss in somewhat detail. But the issue is that if your if the viscosity of your polymer or the photoresist is too high, then even spin coating will fail to produce a smooth and uniform layer. There will be spatial variation of film thickness, which is completely undesirable in the context of proper pattern transfer, and therefore, you would like to have your film after spin coating as smooth as possible. So, in order to achieve that, you essentially need to have some solvent in the system whose prime role is to reduce the viscosity. So, that when there is you want to spread your photoresist on the silicon wafer substrate to achieve a film of uniform thickness, it can be accomplished. So, these are the three key components of a photoresist: the resin, the inhibitor or the sensitizer, which is the photoactive ingredient, and the solvent, which is necessary for not only in a photoresist, but in almost all polymers wherever people apply techniques like spin coating or dip coating. Now, there are essentially two different types of photoresists, or which are also known as the different photoresist tones. The first one is called a positive photoresist, which upon exposure to UV light undergoes structural changes and degrades and becomes more soluble in the developer. So, essentially a developer is also another type of a solvent. It is not a solvent that is used for coating of the photoresist layer, but it is used after the photoresist layer has been exposed to UV light. So, a positive photoresist, if we look at, so it is like this: you have somehow coated a photoresist layer on your oxide coated silicon wafer, and let us say you place a mask here where this part is opaque and the other parts are transparent. Okay. So, if you now shine UV light from the top, very simply speaking, UV light cannot penetrate over these areas, and UV light penetrates over these areas and falls over these zones. For if the photoresist here is a positive, has a positive tone, then what is going to happen, the resist layer over these zones is going to degrade. Okay. So, they are going to these areas, it is going to degrade structurally, which can be in the form of chain scission, that is longer polymer chains are broken down into smaller chains. So, that when you apply the developer, it becomes easier for the developer to dissolve polymer preferentially from these areas, and there is no structural change to this particular area. So, here the polymer sort of remains intact or retains its initial properties. So, now what happens when you now wash or dip this photoresist, which has photoresist layer which has been UV exposed to a developer solution. For all our practical purposes, we will just regard the developer solution to be a special type of a solvent. Please remember that the developer solution is not unique, and typically every photoresist, whether it is positive or negative, has its own developer solution. It is obvious because the structural changes that are going to happen for every photoresist, for each photoresist or for photoresist having different tone is different. So, for example, if you are using a positive photoresist, coming back to the example we were talking about, and now you put it in the developer solution. So, what has happened is, over these parts the polymer, the photoresist layer has sort of degraded, and these areas or the photoresist over these areas become soluble in the developer solution. While the photoresist layer over this area remains insoluble. So, what would be the outcome? The outcome would be this is your oxide layer, this is your silicon wafer, and you get a structure like this. So, over these areas your corresponds to these zones where you had a positive photoresist layer which had been exposed to the UV light, and the material property, there was a degradation of the material property over these zones. So, when this UV exposed photoresist layer was sort of washed or subject to development or was washed in developer solution, what happened is the polymer from this zone and this zone got preferentially washed away. However, since this particular part which was below the sort of obstruction or the opaque zone in the mask, or a zone which absorbed the UV light, there was no change, no structural change, and therefore, when it was washed it did not dissolve away. So, it retained its structure. So, see what has happened here, you had taken a mask like this in which this particular zone did not allow the transmission of UV light onto the photoresist coated silicon wafer surface, and consequently your resultant pattern on the photoresist layer becomes something like this. So, I hope this gives you an idea roughly about, this is the heart of the photoresist process. I mean, while explaining the tone, I actually talked about the in a nutshell about the actual photoresist process. So, the height of this structure what you have created, you can probably guess from where you get this height. Well, probably you understand it. This height corresponds to the height of the photoresist layer you have coated. The dimension of this, the lateral dimensions, let us say x1 and y1, correspond to the dimension of this zone on the mask. Okay. So, first thing you can see is that a chemical pattern which you had on the mask. Why I call it a chemical pattern? Because this zone had some distinct chemical properties as compared to this particular zone, and that distinction in the chemical property was in the form of difference towards absorbing the UV light shined upon it. So, essentially these parts did not absorb the UV light or did not block the passage of the UV light, while this particular area did absorb the UV light and it did not allow the UV light to penetrate, and consequently the depending, since we had taken a positive photoresist. So, there was degradation of the photoresist which were under the areas, or photoresist film which were under the areas through which the UV light could penetrate, and consequently a chemical pattern after development. What happens is a chemical pattern which you had taken on the mask now gets converted to a topographic structure on the photoresist layer. Of course, there are several nitty-gritty details, for example, whether your exposure sort of has a sharp interface, whether everything is during development only the entire exposed photoresist layer is stripped away. One has to also ensure that no polymer from the unexposed area gets stripped away. So, these are some of the critical issues. We might be discussing some of them at a subsequent phase, but in a nutshell this is what is the basic principle of photolithography. You may now want to wonder why it is called a positive photoresist, and the answer is very clear from the figure you see, because this way what you get a positive replica of the original pattern you had on mask. Of course, you now realize that the pattern on a mask did not had a topographic feature, it was more of a chemical pattern. However, the pattern over here you get on the photoresist layer is a physical or a topographic structure. So, similarly so let us now get back to the definition of a, or whatever is written for a positive photoresist. When exposed to UV light undergoes structural changes and becomes more soluble in the developer. The exposed resist is then washed away by a developer solution. An exact copy of the mask pattern is created on the resist layer. I hope now, based on the discussion we had here, you understand how it works. In contrast, probably you now can guess what a negative photoresist will do. A negative photoresist, when exposed to UV light, undergoes structural changes, but unlike a positive photoresist where the structural change was in the form of degradation, here the changes is in the form of polymerization or further cross linking. So, it becomes more structurally stable and it sort of can resist dissolution towards the developer, okay, and becomes less soluble in the developer. I am sorry about this typographic error in the PPT, as compared to the unexposed resist. When exposed, the resist which is not exposed to the UV light gets washed away by the developer solution, and eventually an inverse copy of the mask pattern is created on the resist layer. So, probably you understand what it means if you now have a relook at the schematic we sort of used for understanding the positive resist. Here what is going to happen if you have the same configuration. So, you have a photoresist layer, this is the oxide layer, this is the silicon wafer, and you place a mask. Which again has exactly a similar property. This part UV light cannot penetrate, over these areas UV light can penetrate, and this is now what you are using is a negative tone resist. So, what happens is, so these areas on the photoresist layer sort of gets exposed to UV light, this does not get exposed. So, there is no structural change to this particular zone, it remains intact as in the previous case, as in the case of a positive photoresist. However, what happens here in the previous case, when we were using a positive photoresist layer, the areas that got exposed to the UV light, they underwent structural degradation. In contrast, what happens here is that these areas sort of become structurally strong. Which can be in the form of by something called cross linking. What this is, we will definitely discuss at some point of the time. Now, what I mean by structurally strong is that when you used a developer solution, and we mentioned that developer is sort of specific to each of the photoresist you are using. So, when you used an appropriate developer solution, the areas which were exposed to UV light in case of a positive photoresist preferentially got dissolved or gets dissolved. In contrast, here when you use the developer solution, causes no damage to the areas which have been exposed to UV light. So, no damage, or in other words, the UV exposed areas preferentially resist the developer solution, and the area that is not exposed to UV light dissolves. So, this actually dissolves away. Okay. So, you see that if you are using a negative photoresist, you achieve exactly the opposite thing as you had achieved in a positive photoresist. In a positive photoresist, the zones which were exposed to UV light got dissolved in the developer solution. In contrast, in case you use a negative photoresist, the zones which are not exposed to UV light become structurally weak as compared to the areas which are exposed to the UV light, and when you subject this UV exposed photoresist layer to the developer solution, this particular area preferentially washes away. So, now drawing a similarity, so if this is the mask with which you get started, exactly in a similar fashion like this, you eventually get to a structure on the film surface like this, okay, where the depth of the structure H corresponds to the thickness of the photoresist layer, and this is an cross linked photoresist layer. So, you see you again get a copy of the chemical pattern on the mask, but here the copy is in the form of it is exactly an inverse copy what you get on the film surface, that is you get a negative replica. So, in case of a positive photoresist, now again you can compare side by side, you had a mask and what you got is a sort of a self standing pillar of the photoresist layer on the oxide coated silicon wafer. In contrast, if you use a negative photoresist, what you get a hole in a intact photoresist layer, and probably if your development is good, the base of the hole will expose the oxide layer. Similarly, here if your development is good, the photoresist structure will be standing on the oxide layer. So, this is the key difference in the patterns that you will obtain, that one obtains depending on the tone of the photoresist that one is using. So, if you are using a positive photoresist or a photoresist having a positive tone, you will eventually get to a positive replica. In contrast, if you are using a photoresist which is a negative photoresist, you will get to a structure which is a negative replica. This is what I tried to explain you in a very simple fashion. I hope things are clear to you. So, keep this slide in mind or these images in mind, and this is essentially the basic concept of not only photoresist stone, which is of course the fundamental concept. This is what exactly happens, but this also in a nutshell sort of tells you about pretty much what you do in photolithography. Of course, there are lots of complications because this is a process that is very well utilized or extremely well utilized in the industry. So, there are lots of automation, lots of steps, lots of nitty-gritties, but for our understanding from the engineering perspective, from a chemical engineer's perspective, this is good enough to understand what exactly photolithography does or how it works. Okay. So, you may be interested to note that the first commercial photoresist was a negative photoresist, which was known as the Kodak thin film resist. So, this is this slide now sort of shows you what I have discussed so far. So, suppose this you use this as the photo mask. These are the areas over which the light cannot pass or UV light cannot penetrate. So, this is a negative photoresist layer, this is a positive photoresist layer, and here you see that upon exposure. So, this particular area becomes weaker, structurally weaker to resist the attack of the developer solution as compared to the areas which are exposed, eventually resulting in a negative replica of the mask pattern. I guess now this figure makes complete sense to you based on the discussion we had. In contrast, if you use a layer of a positive photoresist and you expose it to UV light, and then what happens is these areas becomes these areas offer more resistance to the developer solution as compared to the areas which have been exposed, eventually resulting in a positive replica of the mask pattern on the oxide coated film surface. So, this is the key difference between a positive photoresist and a negative photoresist. We will deliberately avoid the chemistry. There are lots of chemical chemistry, lot of research in the photoresist chemistry goes on to enhance its photosensitivity, to enhance the quality of development, so that there are less residues, etc., but we will skip all that for the time being. You can imagine that one of the critical stages in the development or even in the during the exposure stage would be how do you ensure that your this photoresist layer, let us say over here, gets uniformly exposed, because as you get deeper into the photoresist layer, suppose this is a photoresist layer, this is a mask you have, let us say these areas light cannot penetrate, but this area it can penetrate. So, it gets exposed, but the question is that as the light travels through the thickness of the photoresist layer, how do you ensure that it sort of uniformly exposes the entire zone of the photoresist layer below this? There is every possibility that the exposure might eventually lead to sort of structural change of a zone like this. So, which is highly undesirable, because then after development you will not get a structure like this, whatever photoresist stone you are using, but you will land up getting a structure like this. So, which from the microelectronic industry is completely unacceptable. The other possibility is that even if your exposure is proper during the stage of development, suppose this is a negative this is a negative resist. So, you want this area to strip off, it does not strip off, or the entire resist layer, unexposed resist layer does not get washed away, but you get a structure like this. So, there is a remnant photoresist layer that remains due to poor development. So, that is also completely undesirable, because eventually at the end of the day probably you understand now that you need to have an access to the oxide layer, and we saw in the animation, and this is the silicon wafer. So, your final objective is to also get rid of the oxide layer, so that you have an access to the silicon wafer where you can have your doping reaction. But if on top of the oxide layer itself the photoresist layer is not fully developed, not properly developed, and a remnant layer of underexposed or overexposed or unexposed photoresist remains, that is going to spoil your entire process. So, there are a lot of critical details which one really has to worry about, and we will see some of them without going into too much details of the whole technique. So, here is a quick comparison between the different types of photoresist. There are several critical properties one would like to compare. So, adhesion to silicon of course is a very important, or the oxide layer. Positive photoresist it's fair, negative photoresist it's excellent. Relative cost for a positive photoresist is slightly more as compared to a negative photoresist. The developer base for a positive photoresist is typically aqueous. The developer base for a negative photoresist is generally organic. The minimum feature size for a positive photoresist is less than 500 nanometer. Now, this is important. This is what makes positive photoresist, what is written at the bottom of the table. Most present day ICs are fabricated based on positive photoresists. This is where actually negative photoresist has severe issues, because achieving a lateral resolution of less than a couple of micron is difficult with a negative photoresist, and as we told that for the present day processors, of course, one is looking at dimensions of 30 nanometer to 50 nanometer. So, you need to have feature sizes which are very very small, and it's due to this particular reason a positive photoresist is well preferred in the industry as compared to a negative photoresist. The step coverage is better as compared to in a positive photoresist as compared to a negative photoresist, and wet chemical resistance is fair in positive photoresist. This is something that is not the best in a positive photoresist. What exactly is wet chemical resistance, you will soon realize, and at what stage it is needed. In contrast, it is excellent for a negative photoresist. Well, I just already mentioned that most present day commercial techniques preferentially use a positive photoresist. You may want to know the name of some of the commercial photoresists. So, AZ 111 XFS and other variants are positive photoresist. Lot of, if you read research papers, a lot of them use SU8 at the lab scale. This is a very very popular resist, very popular. People actually make patterns on SU8 and then sort of carbonize all them also to create carbon nanostructure or carbon mesostructure, which can be extremely useful in micro batteries, micro capacitors, etc. And SU8 is actually a negative photoresist. Okay. So, now let us get back to the photoresist processing steps. You now understand that the base material, this processing is going to be with photoresist. So, here are the things what we understand. So, you understand what is a photoresist now, and the photoresist processing is going to be on a oxide coated cleaned silicon wafer. We have in our previous discussion or previous classes in the previous class already discussed about the growth of the barrier layer and about the cleaning. So, first you take the as supplied wafer, clean it, then grow the barrier layer. Now, it is ready for photoresist processing. So, you have photoresist. So, the first thing you need to do is before you coat the photoresist layer, you need to do some additional processing of the surface, which can be, you can regard it to be some sort of a cleaning step, but this is a cleaning step not of the silicon wafer, but of the oxide layer. I would not regard it, not sort of officially use the word cleaning, but let us put it as some sort of an additional processing. Of the surface, and this is the surface of the barrier layer or of the oxide layer, which are known as the dehydration and priming. This is primarily done to ensure that you get a smooth photoresist layer on top of the oxide coated wafer, and the adhesion between the photoresist layer and the oxide layer is good. So, firstly to ensure smooth intact resist layer formation, and also to ensure secondly the adhesion is good, adhesion between the photoresist layer and the oxide layer. Okay. So, this is the key objective of the dehydration and priming process. Now, once your wafer is dehydrated and primed, then it is ready for photoresist coating. So, the next stage that comes up, we will again rediscuss it, is the coating of photoresist on the wafer. Okay. So, so next few minutes we will keep our discussion limited to these two critical aspects. Then of course, you can see that photoresist processing comprises of several subsequent steps like soft baking, exposure. We already talked about exposure while discussing photoresist tone. Then development, again this is something we have already talked using the developer solution, and then post development inspection. Okay. So, let us talk about the first photoresist processing step, as we told that it is dehydration and priming. So, before the resist is coated, the wafer must be free from moisture and contaminants, both of which cause a severe problem in resist processing. Contaminants as well as moisture, if they are present on the oxide layer, both of them will first try to sort of hinder the formation of a smooth uniform thin film of the photoresist layer on the oxide coated or on the barrier surface. So, firstly there is a possibility that your film quality will not be good, and also if you sort of can achieve a or obtain a photoresist layer, moisture severely hinders the adhesion between the photoresist layer and the oxide layer or the barrier layer. So, dehydration baking is dehydration. So, you can imagine it is sort of a high temperature processing, or you place your wafer at a high temperature, so that any moisture present sort of or any organic material present sort of preferentially evaporates away. So, dehydration baking is performed to eliminate any moisture adsorbed on the wafer surface, as hydrated surface leads to adhesion failure. That means that there is it sort of as we just mentioned, that if moisture is present on the wafer surface or on the barrier surface, it severely affects the adhesion. Dehydration is usually performed by heating to temperatures between 400 degrees centigrade to 800 degrees centigrade. Typically some standard oven or furnaces are used for this purpose. After dehydration baking, the wafer is coated with a pre-resist priming layer. It is sort of this can also be done by spin coating at times. It is not exactly the photoresist, but it is coated with a it is known as a pre-resist priming layer. That is something is enough if you remember, which enhances the adhesion properties of the wafer. One of the most common primers used for this purpose is hexamethyl disilazine HMDS. It goes by the, or it is more popular by its acronym HMDS. Resist coating must follow as soon as possible after the priming layer or application of the priming layer. So, here you see what priming also means. Priming means that you cover your resist your oxide layer after moisture removal, you cover your oxide layer with another layer, a very thin layer of a chemical which promotes preferential adhesion. So, it can be also regarded as an adhesion promoter. It promotes adhesion between the photoresist layer and the oxide layer. Conventionally, what is necessary to be done the moment priming is done or after right after priming, it is favored or it is desired that the photoresist layer is or gets coated without any delay, which in turn may sort of degrade, or which in turn degrades, the delay degrades the activity of the priming layer itself. Okay. So, now you have a oxide coated and primed, moisture removed and primed wafer, which is now ready for photoresist application. So, this is now ready for PR photoresist coating or photoresist application. Okay. So, the photoresist application is typically, or the photoresist coating on the wafer surface is typically done by a technique called spin coating. It is a very popular, very widely used and a very simple technique also. So, all you do is that you use the instruments are available from lab scale right up to industrial scale. So, what you do, you have something called a chuck on which you can sort of place your wafer, and typically during the, so as you can figure out from the name, it will spin. So, it will rotate at a high RPM, typical RPMs vary between 3000 to 6000 or 7000 RPMs. There are spin coaters available which can go all the way up to 10,000 RPMs, these are pretty well known now. So, one of the, so chuck is that hardware element on which you actually place your wafer first before you dispense the photoresist. Now, one critical issue that is going to come up, what is going to, how are you going to ensure that the photoresist, that the wafer remains on the chuck when there is such a high speed rotation. So, that is typically ensured by a vacuum connection. So, you have a small opening on the chuck which is connected to the vacuum line. So, this suction provided by the vacuum pump or in the vacuum line sort of holds the chuck as it rotates. This is a very standard procedure, very standard technique, and almost all the spin coaters are used in this way. The reason that you do not really want to use something like a adhesive tape here. So, this is the wafer. So, this is that wafer, that primed wafer which you place on the chuck and which is now ready for spin coating, and the rotation starts after you apply a solution of the photoresist layer or dispense the photoresist solution on this wafer. Now, before that we were just talking about the mechanism by which this substrate or this silicon wafer, in this case the substrate is the wafer, is held to the chuck, and typically that is achieved by a vacuum connection. So, here you can see that also in this transparency. So, this is it called the basin or the sort of area of the spin coater where all the operation takes place. So, this is the chuck, if you can see, and so this is the chuck we were talking about, and this chuck is connected to a vacuum line. So, when you place the wafer, this is the wafer here, and turn on the vacuum, because of the suction triggered at here through the opening, the wafer sort of sticks to the or adheres to the chuck even during rotation. So, once the wafer is placed on the chuck, the primed wafer is placed on the chuck and the vacuum line is turned on, it is now ready for rotation, and before that what you now do, you can do it manually, but typically it is done in industry it is also done. So, photoresist solution is dispensed. So, when I say solution, it is actually the photoresist resin and the inhibitor which are now diluted in the solvent we talked about, and it is dispensed. So, once the solution is dispensed, then you start the rotation. So, the whole thing starts to rotate, and what happens is, as you rotate it, because of the high speed, so this is the initially dispensed solution, let us say, and as you try to rotate, so this is the initially dispensed drop, and as it starts rotating, what happens is this drop starts spreading and covers the entire wafer. So, I will repeat the cartoon again. So, this is the wafer, let us say, or the substrate or the wafer sitting on the chuck. On the back side of it, the vacuum connection has now been switched on, so that the chuck does not fall off, and then you dispense your photoresist drop. You may dispense it in a fashion that during disposition itself the photoresist solution covers the entire wafer, or you can dispense it at some location centrally, it really does not matter. Okay. If you are working with a very small piece, maybe you would like to cover the whole substrate during the dispensing step itself. But anyway, as you dispense and then start the or turn on the rotation, what happens is, due to the centripetal force, the liquid meniscus starts spreading, and this spreading is irrespective of, I mean, this is not exactly what you really worry in a commercial photolithography technique, but maybe from the standpoint of spin coating, we may want to point out, or I may want to point out here that when we were talking about the concept of wetting and hydrophobic surface, hydrophilic surface, or a surface with preferential wetting and preferential non-preferential wetting. So, essentially this is a type of a surface which we saw that there is partial wetting, but theta lies between 0 and pi by 2. This is a type of a surface where you had complete wetting. So, and this is a type of a surface which is partial wetting, but it does not really prefer the liquid to spread on it, okay, because the contact angle is higher than 90 degree. So, it would really prefer that the liquid dispensed remains as isolated droplets. So, in principle only by spreading you will not be able to even cast a film on such type of a non-wettable or preferentially non-wettable substrate. You may cast a film, but that film also will sort of have will try to tend to retract. Only in this type of cases you can cast a nice film. But what happens is in spin coating, since you are going in for a very high speed rotation, so you are supplying a significantly higher amount of centripetal force and which overcomes the resistance put up by the surface, by the balance of the horizontal component of surface tension forces. So, this is also important, and in the context of instability we will see that this is an extremely important aspect. So, by spin coating it becomes possible to create thin films on non-wettable surface. Okay. So, here we get back. So, you see that you dispense the drop and you start the rotation. So, the entire drop spreads covering the whole wafer. But there is something more that happens. So, these are the different steps or different regimes of spin coating. First operation of course is that you hold on your substrate to the chuck with a vacuum connection and then dispense the photo or polymer solution or the photoresist solution. Typically one uses a pretty dilute solution, the reason for which will become clear to you in a minute's time. Then as you turn on the rotation, you can actually see that the meniscus is travelling from the center to the edge. Then as the meniscus, advancing meniscus sort of reaches the edge of the substrate, there is a lot of polymer that is splashed out of the substrate. And in the third stage what you see that the fully spread solution, from the fully spread solution there is evaporation of the solvent, which so in the initial stages if you look at this particular figure, what you have is a continuous film, but this is a continuous film of a solvent rich polymer or photoresist in this case. And eventually as you continue with your rotation, and this rotation can be as low as a minute, couple of minutes, that is it. As you continue with your rotation, there is a rapid evaporation of the solvent, which results in the polymer, the solvent being sort of completely evaporating away and leaving behind the polymer in the form of a thin film. So, this is what is this particular aspect makes it possible of obtaining a continuous film even on a non-wettable surface. So, what happens is in the initial stage where you have high solvent concentration, and because of this high RPM, irrespective of the nature of the wettability, whether it is preferentially wetting or not, this solvent rich polymer film spreads on the entire solid substrate. Now, once it spreads, the solvent starts evaporating, solvent rather rapidly evaporates. Okay. And as the solvent evaporates, it leaves behind, however, the polymer which is the or the photoresist in this case, which is the solute in this particular case, cannot evaporate, and it gets gradually sort of deposited on the film surface, okay, on the substrate. Now, once you complete the process of spin coating, towards the end of the process what happens is, even if you have a non-wettable surface, you have a layer of polymer or photoresist which is deposited onto it. In case of photoresist, that is typically not the problem, but there can be various other settings or experiments where you may want to sort of have a continuous film on a non-wettable surface, and spin coating is indeed a preferred technique. Now, this polymer layer, though thermodynamically it is unfavored, looking at the spreading coefficient it is unfavored, because the surface does not want to remain covered with this polymer, but what now happens, these are long chain molecules and there is no solvent. So, they have extremely high viscosity. So, the molecules do not remain labile, they cannot move, because their mobility was essentially due to the presence of the solvent, which, so now you realize the importance of the solvent layer, which sort of reduces the viscosity, allows the spreading of the photoresist or the polymer during the spin coating. If you did, in case there was no solvent dilution, the meniscus will not travel very fast, because the as dispensed polymer will have very high viscosity, and even with rapid rotation the meniscus will tend to sort of flow or move very slowly, or it may not move at all. It may actually form some undulations on the surface and can sort of create a film with non-uniform thickness. But this is very important. So, these are the critical steps. So, you dispense the photoresist dilute photoresist solution or the dilute polymer solution, turn on the rotation, and due to the rotation the meniscus then travels, then you have a continuous film of the solvent rich polymer. The solvent eventually evaporates away, leaving behind a thin polymer layer. And so, this is how in the context of photolithography you get a continuous smooth and pretty thin photoresist layer on top of a primed oxide coated silicon wafer.